Welcome. It's September 2016, and this is episode 59 of the Unseen Podcast. The Unseen Podcast is the unscripted, unedited, for the most part, completely open participation spin-off of the Wow Signal. For more information about the Unseen Podcast, please go visit unseenpodcast.com, where you can find everything you need to know about this podcast, including all previous 58 episodes. And tonight, we are talking about big history, deep time, and just basically time in the large scale. And with me tonight are four panelists. I have Chris Prophet.
Hi.
Hello,
Hi there.
Chris. David Grigg. Say hello, David. Oh, did we lose David?
Hi.
Okay, there he is. Roger Wehbe.
Hi.
Roger's this is your first time on the Unseen Podcast, so welcome.
It is.
And I'll ask you just now, Roger, in a moment after, I'll ask you about yourself a little bit more. And Nick Nielsen.
Hello, Paul, and hello to the Unseen Podcast.
Okay, Roger, who is Roger Wehbe?
You know, I just have an interest in this. I start off and you just look up, you see a lot of stars. Each one of them has a planet. There's life out there, and I just scientifically actually prove it. I think that one day we are going to, could be Tabby Star, you know, it could be something, but I'm interested in it. So that's one thing. That's why Reddit for this star about. But I also have a passion for it overall. Me and my life, though, I mean, I work in advertising. I do a lot of modeling for clients, like in terms of target market. It's a lot of statistical analysis. So, you know, I kind of get when you guys are dealing with like really big numbers. You know, I kind of get where it comes from. You know, that's it. I mean, nobody's special. So I'm just your average guy, but I'm really interested in stuff, you know, and I believe that it's great how it's coming to the masses. People are starting to, you know, really take an interest in astronomy. They're starting to really take an interest in, you know, things that are happening more than around them. That's me.
Okay, great. I hope to get up to average guy at some point myself. Okay, so I tell you, David, can we kick off with you and sort of get your thoughts, and
Sure.
then
Okay. Well, the idea I had to talk about today was about time, and in fact the concept of deep time, which is really trying to get an understanding of how long the timescales are, both of the creation and evolution of the Earth, and in fact the universe as a whole. I thought one way to start off might be to think about the XKCD cartoon that came out recently about global temperatures. I don't know whether the others here have seen that.
oh yeah,
But
yeah. I think have we all seen that? Yeah. Okay.
Yeah.
It's an interesting infographic, and it illustrates the point I guess I'm trying to make of the fact that you have this huge, long, linear cartoon which goes down from 20,000 years ago to the present day, and it's a linear scale. It's not a logarithmic scale or anything like that, and so it's purely linear. And as you scroll down this thing, you see how temperatures have varied over the last 20,000 years until you get to the present day, when you see suddenly this huge spike of temperatures. And the point I'm trying to make about that, I guess, is not to debate the issues of climate change as such, but to say that I think one of the mistakes that people make about climate change is due to this poor understanding we have of timescales. We tend to look at the timescales of the last couple of hundred years and say, oh, well, temperatures have increased, but you know, temperatures have been changing backwards and forwards over the last million years or so. But when you see an infographic like that, it makes you realize that our timescales are all wrong. Something that has happened over a period of a couple of hundred years is a very significant change. We're trying to compare two things which are not not measurable against each other. We're trying to compare the last couple of hundred years with the last 20,000 years. And it's only when you see an infographic like that you suddenly realize that our timescales are all messed up. I think the problem is that we just have a real difficulty in understanding these deep amounts of time that exist in the past. We're so short-lived; it's very hard for us to get a handle on it. And it's similar. The whole phrase "deep time" really came about through the work of people like James Hutton, the geologist in the late 1700s, who came up with the idea of looking at the Earth's geology and saying there are all these very small, very gradual effects that are happening, and we look at them and think, no, they can't have much of an effect. But it's when you get into the concept of deep time and understanding that the Earth is in fact 4.5 billion years old, that you see these effects have enormous impact over that sort of length of time. But it's still very hard for people to get a handle on that and get an understanding of that. So that's kind of where that whole phrase "deep time" comes from.
Yeah. James Hutton is a hero of mine. I mean, he was one of these polymath types who was knew a lot about a lot of things. And back in the time when you could know a lot about a lot, and he was part of the Scottish Enlightenment, and he actually, he one of these people that took a concept of went from thousands. He said the Earth, from the concept they had then was the Earth was thousands of years old. He didn't know how old the Earth was, but he says it's got to be a lot older than that. It's got to be millions of years, and to make that conceptual leap was amazing. We tend to take it for granted now. We talk about millions of years very casually. But
unfortunately, Hutton was not a very good writer, so very few people read him, and it was left to Lyell to actually get people to think in these geological timescales, of which Hutton was the pioneer. Although before Hutton, there was a Danish geologist by the name of Nicholas Steno, who was one who formulated the laws of superposition, which are still central to geology today.
Mm-hmm. Yeah, well, Lyell was certainly the pivotal character in a lot of things. I mean, he influenced Darwin to a great extent. So,
yeah, Darwin took the Lyell's volumes on the voyage of the Beagle with him.
Right. So and Lyell was influenced sharply by Hutton. When Hutton first put in results in Edinburgh, it kind of was to a ho-hum response. Well, yeah, but so a bunch of rocks pile up on top of each other, so what? But it took Lyell to really grab that and run with it. But, it was just 200 and change years ago that our forefathers went from seeing things in terms of thousands of years to seeing things in terms of millions of years. Now, it took a long time after that before thousands of millions or billions of years became part of the vocabulary. But now we're thinking way beyond that. And it's our ability to do math has far exceeded our intuition of time by many orders of magnitude.
I think that's a problem too. I think that it does limit enormously how we look at things and the assumptions that we make about the world. You talked about Darwin taking Lyell's books on his voyage, and of course, it was his concept of learning about deep time, which also led to the theory of evolution. If you have very small changes happening over an enormous stretch of time, then you can go from a bacterium to a brontosaurus. There's no such things as brontosauruses, are there? A tyrannosaurus.
There's a very interesting side story about the passage from geological time to biological time, which was after Darwin had written Origin of Species, then Lord Kelvin, who was one of the most eminent scientists of his age, calculated the age of the Earth and said, well, there wasn't possibly enough time for evolution to take place. And this then, Kelvin there was no science of radioactivity yet. So Kelvin hadn't figured a radioactive decay into the age of the Earth. And then once not long after Kelvin had written, people started making discoveries about radioactivity. And then when you take into account radioactivity, then you get a more correct age for the Earth that corresponds to the possibility of evolution taking place over those geological scales of time.
Yeah, well, Lord Kelvin had state-of-the-art knowledge for his day, right? I mean, he just
didn't know about radioactivity.
A lot of stuff he didn't know about, right? And was it he or said that as soon as we figure out this weird stuff going on with the black body radiation and the Michelson Morley experiment, then we'll have this all settled.
The end of physics. Yes, I can't remember if that was him or somebody else, but yeah, somebody did say that.
And of course, those two things blew away they didn't blow away the old physics, but they resulted in a revolution of physics.
Resulted in quantum physics.
Well, quantum physics and also relativity. Well, although actually Einstein wasn't really that well informed about the Michelson Morley experiment. I think he was just more motivated by other things. But the reality is that that our concept of time keeps shifting and growing. And when Hubble discovered how big the universe really was, we'd already decided that the speed of light was the speed limit cosmically. This was in the mid to late 1920s, when Hubble found that roughly how far away the Andromeda Galaxy was. And wow, people were talking about thousands of light years, tens of thousands of light years. He started putting in millions of light years.
2 million light years, yeah.
Yeah. And now he was a little off because there were some technical issues for that. But in fact, the Cepheid variables were not all the same and so on. But it was essentially correct what he came up with. Well, actually, him and Humason, who didn't get as much credit as Hubble, but Humason did a lot of the hard work at the telescope. But this was less than 100 years ago.
1923, I think, is when Hubble published his paper, but I'm not certain about that.
Yeah, we can figure that, but it was in the 20s. Yeah.
It's fun. In Carl Sagan's Cosmos, he used this Roaring Twenties music in the background when he's showing Humason and Hubble working together at the telescope. So it's a fun little episode.
Yeah, and the reality is, that before that there was a lot of discussion and controversy about maybe these galaxies are only a few thousand light years away.
The great debate. I can't remember who the participants were, but whether we live in an island universe or whether we will live in something much larger than island universe. And
then the biggest galaxy in the sky, one that can sometimes be seen with the naked eye under good conditions, and is quite large, was millions of light years away. That people don't realize to this day how that blew away our whole conception of the size and age of the universe. We knew it had to be a lot older and a lot bigger than anybody had thought up to that point. And so now we were dealing with, and that was just a start. Hubble later further, took those techniques and spectral information and said, well, if the Andromeda Galaxy is that big and it's that far away, then similar sized spiral galaxies that are a whole lot smaller on our photographic plates should be a whole lot further away. And this, it only took a few years for people to absorb this. The universe is enormous. And now these days, we take that for granted, but at the time that was a revolution.
There is a reason though. There is a reason. I'm sorry if you don't mind. There is a reason why the numbers are even with the smaller numbers, it's still really big for people. Like, as I said, it's like you were saying before earlier that, what's the difference between, 1,000 years or 1,000,000 years or something for most people? kind of the same, if that makes sense.
Yeah, it
They're
does.
big
It does
numbers.
make sense. Yeah. Yeah. I mean, you talk to somebody about the pyramids being a few thousand years old, and they go, wow, that was a long time ago. And you go,
Yeah.
well, our first ancestors emerged from the tree of life about 5 million years ago. Well, that.
There's also the old joke in it, whether you remember the joke of some public lecture, where the lecturer is talking about the fact that the sun will grow into a red dwarf and the Earth will be destroyed in the next 3 to 4 billion years. And at the end, he asks for questions, and someone in the audience puts up his hand in a very nervous voice, says, "Excuse me, did you say that the Earth will be destroyed in 5 million years?" No, 5 billion years. Oh, that's all right then. I mean, we don't kind of get a sort of visceral understanding of
Yeah,
these.
the difference between 5 million and 5 billion will not affect real estate prices.
No.
Right now.
To put it in a word, we don't internalize scales of time, and as you've been talking about the difficulty of grasping this from a human scale, I've argued in a couple recent blog posts that we really ought to take the bull by the horns and actually teach at a university level scales of time. Because if you think of kids coming into, well, I think of my own personal development. It took me decades to get my head around what the real significance of geological time and cosmological time were. And you have the different sciences using different scales of time, particle physics using incredibly small periods of time, and progressively getting up until cosmological time. I think it would be really helpful to actually study this in an explicit way and teach time and teach history, not teaching history in terms of the content of history, but teaching how we reconstruct various forms of history. Just like you were talking about the Hubble, we're still formulating the cosmic distance ladder. That's still a work in progress. And in the same way, we're still formulating scales of time. And we're always pushing the boundaries out further, and it's very difficult for human beings to keep it all straight.
Well, yeah, I mean, I remember when I first went to a university as a young person, and I heard lots of people throwing millions and billions of years around very casually. Yeah, it's at 3.2 billion years old, or that's that's 6 billion light years away, or the redshift and that is z equals 2. And I go, wait a minute, you're talking about that as if it were next door. You should almost have like a religious ceremony when you talk about something that's 10 billion years old.
But you have to do that if you're studying galaxies. But the problem comes when people don't realize that when astronomers talk about the universe expanding, they're really talking. Somebody has said that the basic unit for astronomers is galaxies, and most people don't even think in terms of galaxies. They think of stars. And I can think of the first time as a young child when I heard that the universe was expanding. I actually became sad because I thought interstellar travel would be more difficult, and it never occurred to me that the stars in the Milky Way would be about the same distance from each other, always changing, of course. But what he really meant was that all the galaxies were flying apart from each other.
Yeah, it's the distance scales are hard to get your head around. I recently did something in the WOW signal where I wanted to compare for people how far away the nearest star is compared to our solar system. I said, well, if you go, it took New Horizons 9 years to get out to Pluto. It went in a powerful rocket, and it was one of the fastest moving things humanity's ever created. And it took 9 years to get out there. That's 1/10,000th of the distance to the nearest star, and approximately round numbers. And I had actually done that calculation before. I sat down and did it, and I go, wow, 1/10,000th. So, and it's not, you can't scale that up. You can't say, well, we'll take New Horizons 90,000 years to get to the nearest star. It won't. It'll take a lot longer for wherever it's going. But, the reality is that that even that scale of 1 to 10,000 is very hard to visualize. You have to tell people, well, okay, think of going down to the grocery store. Okay, that's about a mile. Okay, now think of going to Tokyo. You get maybe that would help. What if you had to drive if you could drive to Tokyo, which you can't, but it would take you. On a plane, it takes about 14 hours to get to Tokyo. So, that kind of thing is and if you're on a plane flying over this territory, you get to the grocery store in seconds. So, but even that is difficult to compare those scales. I mean, as humans, we are very well adapted to think in terms of months, years, lifetimes, how long it takes a baby to go from being a baby to being an adult. Maybe in the old days, it was more like about 14 years. That kind of time scale we're fine with, but beyond that, it's just math.
I got a good comparison for you, Paul. It's the plate tectonic thing, basically. Yeah. They move a couple of inches a year, but in effect, the continents sit on top of those tectonic plates. They've gone around the world several times, each one in the time since the Earth's come into creation. It's just getting that scale into your head. You can't quite get your head around it until you
I remember
look at the effect.
I remember it's about 11 years old, looking at the National Geographic map that showed not only the continents but the ocean surface, the ocean floor, and thinking, gosh, South America fits into Africa pretty well if you just kind of slide it over there.
Mash them together, yeah.
But how long would that take? Well, a few 100 million years.
Yeah.
But
I mean, you're right. When we got no idea what we had for lunch last week, how can we get our mind around that sort of time scale?
I was just thinking, David Bowie died earlier this year, and David Bowie was a vibrant young pop star last week, wasn't he?
No.
Okay, well maybe that was 40 years or 50 years. But 40 years goes by in a flash, but to a young person, that's a very, very long time. But even to an old person, 50 years is a long time. And, but to us, and it seems like my kids were born last week. And yet the youngest one is 12 now. But still,
it points up how inadequate our human understanding is. Our lifetimes are so short, and the distances we cover are so small compared to the reach of the universe. It's just extremely difficult to.
Well, that's what I wanted to bring up, though. What happens when we no longer have aging? I may miss that boat. I probably will, but. When we figure out aging, which I think we're probably a generation or two away from figuring out how to cure it, we no longer age. We maybe live for hundreds, maybe thousands of years.
I think we're going to get uploaded. I mean, really, I don't think they're going to. What are they going to do? Replace every single organ and whatever?
Yeah, that's the idea. Yeah, I mean, not replace it, but just sort of keep it from getting the aging process. I think we're about maybe 20% to understanding that very well. In another 20 years, we'll understand it extremely well. And then perhaps the next generation will know how to stop it.
Well, then there's other problems. Now you have a population that doesn't die, but continues to multiply.
Well,
that's not a problem if you're expanding into space.
Well, if you're expanding into space,
it's not a problem if just barely a replacement, like most of the populations in the developed world are now, right? I mean, look at there are places like Italy which are begging mothers to have children. So
all throughout the industrialized world, birth rates have fallen precipitously, and we're seeing the increases in the least industrialized and the poorest parts of the world. But I sometimes like to say that 7 billion people is a lot for one planet, but it's very little for one galaxy and a drop in the bucket for one universe.
That's true.
That's all very well, but you've got to be able to expand out at that sort of rate. And the thing about immortality is that there is no need for replacement. Now, the reason that Italy's population is declining is because they're not keeping up with the replacement rate. But once you have immortality, there's no replacement rate.
But what I'm saying is that
since infinite
is our fertility is dropping, primarily because women are delaying childbirth everywhere in the developed world, and even in the third world, or the so-called developing world, the women are the fertility is dropping dramatically. There aren't as many babies being born per woman as there used to be. And
I don't think you could just blame the women, though, because I think
I'm not blaming them.
If they got married, if they had somebody who was willing to marry them and stay by them while they're having kids, they might decide to have children earlier.
No, it's not that. It's not that. It's that they realize that their lives are better without a house full of children, and they know the motivation for having lots of kids is rapidly disappearing.
Well, if our biotechnology reaches the level where we have mastered mortality, we certainly also will have mastered the artificial womb. So if we want to produce more people, we can, and if we choose not to and remain at a stable equilibrium population, we could choose to do that also.
Yeah, I mean, I hate to think of sex disappearing, but that may actually, there's. To our generation, that seems impossible. But
even if we do develop a form of immortality, short of a complete digital uploading, as Roger suggests, we'd really may be talking a few thousands of years, which is still a tiny, tiny, tiny fraction of the length of time that the universe has existed, and it's still a tiny fraction of the time it would take to expand into the rest of the universe.
Yeah, but I think there's a couple of consequences here. One is more short term, is you'll find a lot of young people much less willing to die for a cause because they could live thousands of years, and which is good, I think. You read about World War I, where you had all these fine young men who just threw themselves into machine guns for king and country. I think that's already fading, and I think will continue to fade. The other thing is that if we have thousands of years to live, our sense of what is too long a project or our investment horizon will greatly expand. If I'm going to live 5,000 years, I'm thinking 500 years might be a good investment horizon. All right.
We will know. Sorry, go on.
Well, that's what I'm thinking. I mean, it's just that if it takes a project hundreds of years to complete, that's fine. If I'm going to live 5,000 years, if I'm going to live 50 years, it's not.
There is no doubt in my mind that if you live that long, you'll start taking on huge projects. You'll see mankind building Dyson spheres. I mean, if you live that long, you have the patience now to do it. You have the time. Let's look at us. I mean, as a species overall, from the first year, we're not even walking. We need consistent care all through our younger years. We only have a very short, productive life, and most of that's still learning. People are still going to college, all until the mid, their mid-20s or longer, depending on how far they go. And then you have at that point a short working period and then a retirement period. It's a very short period of time these people work. That's how long. Like nobody's going to take on a project where it's going to take 10 generations for it to get done. It's just that's what the problem is. I think if your lifespan's longer, we will build gigantic things. Like Hoover Dam will look like nothing, and we have a nice Dyson sphere. We can build one.
And with projects at that scale, civilization could be made effectively immortal, as would the agents who are behind that civilization.
Okay.
I mean, the
Change
biggest
everything.
example is generational ships. They become one generation ships, don't they, for interstellar? You can start thinking about that if you got that longevity.
Yeah, I've always been very,
kind of
very
get
skeptical of generation ships idea that, we'd send out a big space ark and, the people on the space ark would have children and they would have children and they would have children and so on until, without any population issues, until they arrive at the destination. And then they would somehow realize that they were supposed to be there and colonize the planet that was at the destination, assuming it was colonizable. Somebody wasn't already there.
Exactly. But if they're immortal, they remember exactly the reason why they got on in the first place. Hopefully, unless their memory's completely gone.
Well, there is a way to actually. It's not a way to test it. I'm saying this. The theory you just described, might actually happen if the faster you go, time would slow down in that ship, right? So you can make generation ship as long as you get really close to the speed of light.
Yeah, but I'm skeptical the way it can get that close to the speed of light.
It's no longer a generation ship. If it's going a relativistic velocity, because it's going to be generations back home, but not generations for those on the ship.
My thing is, if you wanted to pretend we wanted to increase our exploration of space, if we were able to go that close to the speed of light, you would see volunteers, because at least in their lifetime, if they wanted to travel to Alpha Centauri, if we can really get there and if it's 4.5 light years away, if we can get there in 7 light and to what would feel to them as only 7 years, people would be stepping on that. People would try it. I mean, I think that would make it a single generation ship.
Yeah, well, I agree with that, but I mean, we don't really have any idea how we would do that. But not that should be an obstacle to starting. But
Right. I mean, there are various things they're playing around with, like at NASA Eagle Works. They're looking at space contraction with
but that requires negative energy densities that are just absurd. I mean, stellar masses.
Well, actually, I think they've brought those down a bit. They were talking about solar masses of power they required, but now they're talking about maybe tens of meters or even meters.
It's still ridiculous amount. I mean, even Albuquerque has said this is never going to happen. It's just a mathematical nicety. It's not
for now our energy levels of our physics aren't up to that level yet, but that doesn't mean they will never be.
Well, or maybe we'll figure out a back door to the whole situation, but I don't want to rule out that we'll ever, but it's clearly not easy to travel faster than the speed of light, or otherwise we'd be colonized by now.
We don't have to. We don't have. What I'm trying to say is, we could reach almost anywhere in the local area. I mean, if we could get just a hair under the speed of light. You don't. Once
you get up into relativistic velocities, above 90% the speed of light, you don't have to restrict yourself to the local universe. Carl Sagan observed a while ago you could make a circuit of the known universe if you've got that 1G starship that can get itself in a few years up to a relativistic velocity.
Yeah, when I was a teenager, I used to dream about that, but
that was Paul
I still do.
Wasn't it?
Well, I know it sounds like hype, but I'm telling you, I think that just getting to that speed, like Star Trek and science fiction and whatever, they have this warp drive. It probably that I don't think we'll ever get past the speed of light, but I think we could eventually. One day, someone's going to think of a nice light sail with a real super strong, thin material, a very powerful power source. And that thing is going to get to 99% or something close like that. I just think it'll happen one day, maybe not my lifetime. But I think once you start reaching speeds like that, we could populate the whole galaxy. We could expand.
Well, okay, that raises the question of why the galaxy is not populated by somebody else right now.
Everybody has a theory on it. It's
well, I mean, I don't think I'd use the word theory.
Yeah.
More
solutions.
The simplest explanation is that we're the first.
Or that it's really hard to populate the galaxy.
It could be.
Well,
really
but it doesn't
hard.
seem that hard, does it? It doesn't seem like the difficulty is so difficult. But yeah, my bet is on we're alone.
Well, we're only 200 years into the Industrial Revolution, so we've only had industrialized technology for a couple hundred years. If we extrapolate a few hundred more years of industrialized development, there's no reason that if we are talking about one and only one technology that might be our hope to get to the stars, then it'd be iffy. But anybody who reads this literature knows that there are dozens of ideas, whether it's fusion or antimatter or wormholes or manipulating gravity or even something like the M drive, which I know some people hate and other people think is going to be our salvation.
I hate it.
Take your pick. But
they're putting that in orbit. They are going to test it.
Well, no, they're not doing that. That's just a paper thing.
I think they're going to bring it out in November, though. The paper for NASA, they're going to publish. It's been peer reviewed, so I think you better not read anything in November, Paul.
No, I will, and you know what? They still have not solved the problem that they're violating one of the most basic symmetries of space, and that a whole lot of good physics, has very well verified physics, depends on. So,
I did hear one possible explanation, which was rather interesting. There was like a Finnish physician. He said these photons bounce backwards and forwards in the frustum chamber, and essentially they pair off, and the electromagnetic proportions of each one cancel the other. So essentially, the photons have no EM, and so they can escape the frustum chamber.
No.
As invisible light. You see, it's invisible light.
This is much more fundamental than that. This is much more fundamental than that. The symmetry of space with respect to translation. It's extremely fundamental. You cannot get thrust that way.
Forgive me for mentioning the M drive, but the only point I wanted to make is that we don't know which one of these technologies will ultimately be practicable.
Well, but possibly zero, possibly none of them.
Possibly zero, possibly none of them. But when you've got that many options, and the fact that if you're willing to take a long time to travel to other stars, like as long as it'll take Voyager to get to another star, you're still talking about, once again, we come to time scales. 40,000 years sounds like a lot to us, but in the time scales of the evolution of stars, colonizing the galaxy at 40,000 years between each probe going from one star to another still accomplishes the task in a few million years.
As Jeffrey Landis pointed out, like 30 years, 25 years ago, whatever, you cannot have a top-down program to colonize the galaxy. Each colony must in turn decide whether it wants to proceed to the next colony, and it's a completely bottoms up situation, which is
unless it's automated. With
even if it's automated, probes. Anything that that can be automated to that level of complexity is going to make its own decisions, and so.
But if its primary imperative is to reproduce and send out further probes, then certainly there will be some failures where that doesn't happen.
Yes, many, I think, because it's really, really hard to build a self-replicating machine. Nobody's done it.
It is now. We've never done it. That's one thing biology can do that we can't do.
We can't even get close. I mean, you say somebody build a machine that I can send out into the wilderness and can replicate itself. They can't even get 1% of the way to that. And because such a machine would be extremely complex and extremely intelligent and extremely autonomous, and it would make its own decisions about what to do. And it may get there and say, screw this. I'm happy where I am. I've got plenty of materials here. And,
only if it has free will.
Well, let's not get into free will.
Such a machine would be very dangerous, I think, don't you think? Because if it's smart enough to do what we're saying,
the whole gray goo issue.
Why wouldn't it wipe? Just either replicate using every bit of material.
Why do I have to go to another star? I can just wipe these people out and turn myself.
Yeah, that's right.
Yeah, well, I mean, that's the problem. The energetic requirements to go into another star are so intense. The amount of free energy you have to harvest is so great that you don't do it because somebody 5 million years ago tells you have to do it. Because you're going to think for yourself. You're going to think, what do I want to do next? And it doesn't matter if it's a machine or one of our biological descendants, or some combination of the two, which I think is more probable. So, if you build a machine that is as smart as us, it basically is us.
Indistinguishability.
Well, in terms of it's willing, it's rebelliousness. Yes.
What was Stargate replicators? Right?
Look, I have a 15-year-old in my house. Okay, she doesn't do anything we tell her to do, right?
Well, it's not a perfect
we made her, but she does not respect our will. And I think any robot that could fly to another star and replicate itself is at least as complicated as my 15-year-old.
I agree with Paul. I seriously do. I think that if you're going to build something that's doing all sorts of, it has to do a lot. I mean, a lot. These probes that from what I described, how it's described to me, they have to do a lot. They have a lot of decisions to make. They need to be able to effectively navigate, harvest, use, build, collect the resources. By all definitions, I believe they would be considered alive. I think so. Or else, what else? Why is it out there then? If it has no reason to, it's not going to go and burn a bunch of resources for no reason.
Paul is saying that's the question it would ask itself. Why am I doing this? Why am I here? Where am I going?
It might even kill itself because, it's like a depressed teenager. But, these things are going to be so complex, we won't be able to specify their behavior.
So do you consider this a fundamental argument against the possibility of a von Neumann probe, or is this just a contingent thing that anything that gets that complicated?
I think the von Neumann probe is a toy model. It's an interesting mental lens. It is not a model.
It's a thought experiment.
Exactly. It's interesting, just like the Fermi paradox is interesting, but it's not the end of the argument. It's just the beginning. It's just the beginning.
How about Nick Bostrom's thing? The simulation hypothesis.
Well, that's kind of different, don't you think? I mean,
that's a bit to chew off. That's a rabbit hole. I don't think we want to go down in the same episode as Deep Time.
Well, it's all about the mice, as we know. So let's move on to the next topic.
Just before you move off the interstellar sort of thing, it seems to me that Gene Roddenberry might have been spot on, really, with his analysis. The universe could be full of advanced civilizations, but what really is their motivation to come here and give us a whole load of enormously advanced technology when they've got exactly the right idea about what we're going to do with it? We're probably going to kill each other off, and if we don't do that, we're probably going to kill them off. So it just makes a lot of sense just to have a sort of federated interstellar community where they respect each other's rights and they don't interfere with developing cultures or each other's cultures, basically. I mean, that makes a lot of sense to me.
That's called the quarantine hypothesis, isn't it? I mean,
or the zoo hypothesis.
The zoo hypothesis.
It's also, what the weird thing is, it is also called the prime directive. I mean, from the other side.
Well, in the fictional world, it's called prime directive.
Yeah, that's what I mean, though. I mean, from that Star Trek, I believe that was based on the zoo hypothesis.
See, this is one of the things that where the deep time thing I think becomes interesting when you look at the SETI issues. I mean, we look at these Star Trek episodes and a lot of science fiction, and when you think about it, you really have a whole bunch of alien civilizations who've all arisen roughly at the same sort of time, or roughly at the same level of technology. Certainly, that's sort of popular science fiction. But the odds of that are incredibly low, because because of these huge timescales we've got since the origin of the universe, sorry, the origin of the galaxy at least. The odds of two civilizations actually being around at the same sort of time, unless one is completely
with roughly equal weapons and shields,
with roughly equal technology, the odds of that are millions to one, literally millions to one.
The odds against it are high unless there is a Goldilocks moment in time, which could be considered one interpretation of the anthropic cosmological principle.
Yes. Or you have the idea that's in Stephen Baxter's novel Space, which is that there's a resetting event. There's a collision of two neutron stars or magnetars or whatever, which essentially wipes the galaxy clean of life at a particular point not very long ago.
And you can have that with
have arisen from
okay,
there.
so nobody here has seen Star Trek 4. Or is it 4? Yeah, I think it was 4. Where they basically we're all seated from the same source, but
panspermia.
Yeah.
Yeah. Well,
so obviously that's the answer, because it was in a movie that I saw.
But actually, it actually occurs in the original series from the 60s too. There's one episode where Spock says, "Well, why are all these humanoid species all around the galaxy?" It's the Indian episode where Kirk, of course, falls in love with an Indian maiden, and there's an obelisk on the planet.
Yeah, well, that. That's probably the answer. That's probably the answer to all this. Captain Kirk seeded the whole galaxy with
my wall has
his descendants.
The reason they're all humanoid is so they can all fit it. We can dress up humans in costumes to make them look like aliens.
Or so Captain Kirk can have sex with them.
Yeah, that's right.
Well, 50% of them, I don't know, maybe.
Well, I think that David's right. I mean, any collection of civilizations we have in our galaxy or any other galaxy is likely to be of widely disparate ages. Now, levels of advancement, we don't know that's linear, right? That could reach some peak and then drop. There's some notion that they may be in decline. They may be descendants of a very, very advanced civilization, but they have the technology, but their ability to maintain it is slowly eroding. It could be lots of things, right?
Could we be at just a very backwater area of the Milky Way?
Yeah, we could be. I mean, one thing a couple of years ago, I interviewed Daniel Carton, who's done some analysis of, colonization using
that percolation theory.
Well, yeah, he uses percolation theory based on Jeffrey Landis's original idea. Jeffrey did not actually sit down and do the numerical work. He kind of just threw the idea out there in a paper. And then Daniel Carton, among others, have sat down and actually done the hard calculations. And depending on what you assume about how likely it is that your colonizers will recolonize, you can get big gaps, big voids in the colonization space, and that's completely reasonable based upon realistic assumptions about how long a starship can travel and so forth. You have to make a lot of assumptions, so it's not definitive, but if you assume that a starship can only last so long before it has to stop and get repaired and let the colonists off, and you assume that there's a probability less than 1 that they will continue on to the next colony, then you can get these big gaps. And how big the gaps are depend on those numbers. And we could be in a bubble. Now, if the more colonizing civilizations you get, of course, the harder that is to explain. But if there's only been one or two, we could easily be in that gap.
Frankly, it seems ridiculous that there's only been one or two. Because, I mean, just look at the basic physics. I mean, the universe has been around, 13.5 billion years? The first stars appeared maybe 500 million after the formation of the universe. There would have been very highly radiant, very active stars, but they're essentially just hydrogen. So they're all fuel. So they probably burn out relatively quickly. Then they turn supernova, throw, elements, more advanced elements all around the universe. So you've had the elements for life all there within the first billion years of the galaxy, the universe's existence. So,
but not at the same rate. No,
not the same rate as now. But they were there.
Metallicity slowly rises over the age of the universe.
Not only that, but you've got all these, or nearly universe, you got all these big gamma ray bursts, sterilizing large chunks of each galaxy.
The reset button for life. Yes.
Yeah, and not, but. Even given that life is all over the galaxy, which I think is actually likely, but just an intuitive sense that I have. I can't prove it to you, but life is all over the galaxy. Maybe even sentient life is all over the galaxy. There's a huge jump from sentient, even technological life to interstellar life. That is a massive leap.
Yeah.
To me, people don't get how big that is, but it's really big. And the motivation is never going to be top down. It's never going to be, let's go there to make a profit, or let's go there to be their masters and rule them. It's always
never. And even if you posit enough civilizations, don't you think it'll be a bell curve of motivations?
No, I mean. Well, you're going to be surrounded by stars. The early civilizations that could do this, surrounded by stars that they have no idea whether they're populated or not.
I disagree with that. By the time we have the technology to build a starship, we'll have a very good idea of what's about the neighboring stars.
Well, and the likelihood is that we're not going to find another civilization there. And if we did, I think if we could build a civilization to survive that long, it's not going to be a warlike civilization. It's not going to be a civilization that's go kick their ass and take over their planet.
I don't think we can draw that conclusion, but I'd like to mention there's a paper that caused a stir last year when it was published called the Globular Cluster Opportunity, in which the authors who presented at a conference and then wrote a paper on it said that because the stars in globular clusters are much far closer together, you could have an interstellar civilization at a lower level of technology, so that these were particularly good spots to look for interstellar civilization.
Oh yeah, I remember that paper, and I think that's actually a pretty good argument.
Except the galactic ecology in a globular cluster is nothing like what it is in the plane of the Milky Way. And you've got a bunch of blue straggler stars, but you don't have this population of recurring, recycling, metallicity of increasing.
Well, but it passes the galactic plane every few 100 million years. It could pick up enough elements.
That's true. That's true. They interact with other galaxies.
So they could have decent, and recently there was a discovery that a lot of black holes in a globular cluster, so which suggests larger stars that could have recycled some elements. So it's entirely possible what we're seeing we can't see that many globular clusters. We can only see the ones that are near us. It's possible they went through an earlier evolution phase where they had a lot of supernovas, and they're done with that now. And what we're seeing is just what's left over. And some of those stars are extremely ancient. They're almost as old as the universe. But in fact, when I was a student in the 20th century, there was still a bit of a puzzle as to why some of the stars in globular clusters seem to be slightly older than the universe.
There are still a few paradoxical stars that appear to be older than the universe.
Well, that's more of a challenge to stellar evolution modeling than it is to the age of the universe. But the idea was, some of these globular clusters have extremely ancient stars, but they also have some newer stars, and they could very well have civilizations in them, and it's hard for us to ascertain that. There's really not much we can do to discover those with our present level of technology. And that's true. The stellar distances there are much shorter. They could travel.
Don't you think though that one of the arguments, which I think is an interesting one, is that if a civilization has been around, again for deep time, if a civilization has been around for 1 billion years, say, surely by the end of that sort of period of technological development, it would be able to make changes to its stellar neighborhood or its immediate neighborhood that would be obvious to us now, and we don't see those.
Well, but I don't, because I'm not. First of all, I'm not sure that there's a continuous development of technology that keeps getting better and better and better in some linear fashion. And second, it's very top-down thinking. It's saying, well, we'll dominate our star, we'll dominate our galaxy or our globular cluster. The only thing we know that we don't see are extremely dominant civilizations that take over a large chunk of a galaxy. The rest we don't really know. The search space is too big, and we haven't covered very much of it.
Unless it's consciously left as a wilderness, in which case we might be in a backwater, as was suggested earlier, which I called the wilderness hypothesis in one of my WoW signal bursts.
Right. The wilderness hypothesis is that we're sort of like a national park, right?
Well, we could be a wilderness in a couple different senses. We could be a wilderness where we just happen to be passed over in one of those colonization bubbles, and they didn't get to us. Or we could be a wilderness in the sense of being purposefully set aside as a wilderness area.
Yeah, well, the idea of the colonization bubble is that no command and control can travel faster than the speed of light. So something that's hundreds of light years away, you basically can't control it, you can't command it, you can't direct it, you can't give it a purpose. So ultimately that peters out over relatively small distances cosmically.
But if it carries with it the technological expertise to re-engineer planetary systems and whole neighborhoods of stars, then that's what was implied earlier would be visible from a distance, and we don't see it.
Right. Well, I mean, the Jason Wright's GHAT paper that came out last year, looking for galaxies where over 80% of the energy is captured for a civilization. Didn't see those, but why would we see 80% of a galaxy? If you think about it, that would require command and control over timescales of hundreds of thousands of years, which these are beings that presumably can formulate very complex thoughts in microseconds. So, that's to me it's
not plausible. Yeah, I agree.
It's way too top down. You have to come up with a self-organizing system that would be and what the signatures of that would be. We don't really, and that's extremely hard to understand. We don't even know why starlings flock the way they do, or why bees form colonies. That kind of thing is, self-organizing systems like that are very difficult to understand from a first principles point of view.
You might have put your finger on it why we're not seeing anybody here right now, because the Earth is a very distinct place. It's a radiation-free oasis because of the magnetosphere and a thick atmosphere. I mean, for all we know, there's alien civilizations which have bypassed us thousands of times because we haven't got a nice, rich radiation bath for them to live in. It could be that we're really distinct because we've got a very strange way of living compared to, the norm. I mean, radiation is everywhere out there. It's just an example about how completely different the life might be out there. And
others said the economic argument for coming to Earth might be very poor. It's not profitable. So the only reason for coming to Earth would be to explore it or to communicate with it, but not to which they can do from a distance.
You sure they don't want to take us as slaves to work in their mines?
They only exist to serve man.
Yes, yes.
That was
but it does raise the issue, doesn't it? Why would we go to another star? Why would we try to colonize another star system?
Yeah.
Is there an economic reason? I don't think there is.
No, there is not. There's not an economic reason. You can't export your population problem to another star.
No. But as Roger said earlier, if you had the technology, people would make use of it. Maybe not. Even out of 7 billion people, if you only have 1% that's interested, you're still talking about 70 million people. That's a lot of people.
Well, here's the thinking about. By the way, I'll recommend this later in my recommendations, but I recently heard a discussion about why do interstellar travel with one of the leading researchers in the area, and he said there's no business reason, there's no top-down reason to do it. We just do it because we want to do it, right? But look at it from a Darwinian point of view. Whoever does it, that's the civilization, or not civilization, but that's going to be the species or the descendants of the species that's what you're going to find in the galaxy. The species that wants to explore and move out and try in spite of incredible obstacles. And these obstacles are very, very large. We can't, I don't want to understate it. Interstellar travel is really, really hard. It takes enormous amounts of energy. It takes technology way beyond what we have now. And people like the Breakthrough Starshot Initiative are looking at sending, something, a few grams out to another star. But if we can figure that out, maybe we can figure out how to send a few kilograms, and then maybe ultimately enough to send enough information to reconstruct a human mind. Like Roger was pointing out earlier, we might be uploaded. If we were uploaded, we could be uploaded into a very, very tiny volume and a very, very tiny mass.
That's actually why I believe that. I believe that for interstellar travel, for longevity, for a whole host of reasons, it would be more. Look, remember how I told you guys like how I work in advertising? I do a lot of modeling for computers and stuff like that, and for networking and whatever. I think uploading to a cloud, if I'm going to look at it like this is my job, if I had this, I would say that the best way to do it would be to convert everybody to a digital environment. If you're going to do it that way, that way you can have multiple redundancies. If they're in a digital environment, a person could theoretically take control of any device, a robotic device in your house or wherever you feel like doing it. You're not tied to one unit. You can go to anything you need to. It's easier to maintain, keep everything in shop in order than 1,000,000 little robots or whatever. That's how I think you can send people or versions of them throughout the stars, and there's no time issue. People can live forever in that environment.
It seems to me, though, that's an argument to say why would such an entity already uploaded into a computer system, which could essentially create an infinite digital environment, why would they be bothered to travel? Why would they need to travel? They're already digital. Everything that they possibly want can be supplied to them in informational form. And they really don't need to go to another star.
That might be the answer to the Fermi paradox.
Yeah, it could be.
And that is what John Smart calls the Transcension Hypothesis, that intelligence becomes much more dense and approximates the environment of a black hole in order to concentrate its processing power in virtual environments, which would be no reason to ever go beyond that.
Yeah, well, Vernor Vinge's written a lot of stories about transcendence, right? I mean, not a new idea.
I would believe, because the costs are very, very high to go from where we are to the nearest star, as Paul pointed out. It's not a cheap endeavor. It takes a lot of resources, a lot of time, a lot of money, and in order to do something like that. So then at the same time, if you look how fast technology progresses on a digital front versus how fast it goes mechanically, I can more easily envision being uploaded than traveling. I'm not saying that's what's going to happen. I'm saying, though, in our current state of technology and how fast artificial intelligence is progressing versus how fast space travel is. Space travel is progressing. We're seeing multiple private companies launching satellites and refueling the International Space Station and ferrying people up and down. That's happening. But at the same time, Google is going a lot quicker than SpaceX is. I don't know how else to describe it.
I think you're right.
Yeah. So that's where I think that's the direction we're going. And
well, yeah, I mean, let's remember in the, well, I don't know if you remember the 60s. I do. We all thought we'd have jetpacks by now.
Yeah.
You don't have a jetpack?
No.
Well,
Where's my flying car?
Yeah, I know. I don't have a flying car or a jetpack, and I'm sure I'd kill myself within 10 seconds if I had a jetpack. But the reality is that we're really good at mastering information. We're really not so good at mastering energy. We're slowly getting a grip on energy. We are rapidly mastering information.
It's the money, basically. That's where the money is. You can work information and you can make money out of it straight away. If only space exploration was like that, we'd be at the end of the solar system.
Information is right now constrained by is not constrained by physics yet. It may be at some point, but energy is, right? Energy is up against the laws of conservation of energy and momentum. So
there will be demand too for space exploration, for mining. A lot of those asteroids, there's stuff in there that would be fantastic to have back on Earth, material out there. You'll have mining operations, you'll have space tourism, you'll have possibly even and eventually terraforming in, Mars or anything that we possibly can. But the thing is, I vision by that point, you will have an option. Do you want to be uploaded? Do you want to do this? Do you want to have a robotic body?
Yeah, I mean, uploading raises some interesting philosophical questions, like who is that? But I think that it's interesting to see how these two things are kind of developing in parallel. And the real answer to space exploration is we're not doing it because there's a compelling economic reason. We're doing it because we want to. And because
it's a genetic imperative, basically. We've always expanded as a species. Always some small part of the clan has sort of broken off and gone a little bit further, and that's exactly what we're seeing in space. It's in our genes, basically. That's the only reason.
Yeah, I think the first trillion.
You're probably right. It is. It probably is in our genes. It really is.
Well, yeah, we're a species that likes to sort of poke around and see what over the next hill, right?
Yeah.
And I think the first trillionaires on Earth will be asteroid miners, but only after lots of failures and people going bankrupt. But the once we have that economy built in the solar system, that's when we'll start asking ourselves where to go from here. But we'll do that not because because people like Elon Musk want to do it, not because we feel like, here's the business. We'll write a business case for 15 years payback on return on investment. We're never going to see that. I mean, well, we might see it, but it would be complete nonsense. Well,
that's what he tells his investors whenever they roll up and give him some money. He says, look, you can have your money back after we get to Mars. Right, so which causes some chuckles.
But your investment horizon has to be, instead of 15 years, which is sort of the normal thing now, right? More like 30, 40, 50 years. And that's going to have to keep going, getting larger and larger. But the reality is, when you ask somebody, why do you do something? Why do you make money? Why do you want to get rich? There's always more questions behind that. And so you ask yourself, why do we want to explore space? The answer is because we want to explore space, right? Not because,
because it's there.
Not because we're going to exploit our population issues, which are actually, I think, considerably less of a worry now than they were 30 years ago, but not because, ultimately, hundreds of millions of years now, they'll be concerned about our sun turning into a red giant, but nobody's really seriously concerned about that now. It's going to be more because we want to have interplanetary species.
Well, it's a backup, isn't it?
It's a backup, but there's no. You can't make a business case for that.
No, but you can make an existential case for that.
Yeah, that's right.
I actually was excited. I actually really excited about Proxima B. I viewed it that not me, but ancestors a million generations down, maybe that could be a backup plan for them. It's a different solar system. It's a habitable zone. You don't know what it is. It could be Venus, But it was nice to see that there's a back. I always thought it could be a backup. That's what I thought of when I first saw it.
Well, certainly if we're going to all become digital, then sure as heck we'd all want a backup, wouldn't we?
Yes.
Yeah. And I suppose the other thing about interstellar travel is I'm thinking of Nicholas Negroponte's book Being Digital, which was in the 1990s, where he talks about we should change from moving atoms to moving bits. And that's really has been the trend of the last 20 odd years or so, is that we've started to move bits rather than atoms. And maybe that's where...
Well, we're moving atoms though, too. We're getting better at that.
Yeah.
Look, I could just tell you, my car, it runs on gas. And I know electric cars are coming, but it took 100 years to move from gas to electric, and we're still not there yet. Internet exploded in the mid-90s. I know it was invented prior, but it was commercialized really in the mid to late 90s. Cell phones only exploded in popularity, which is an extension of the internet, of course. Just, I would say the smartphone would, since 2006, 7, something like that, for the past 10 years. So 10 years into it, we had the internet. 10 years later, everybody's connected to it via a mobile device. The technology continuously moved faster and faster on this front. This whole time this is happening, I probably burned 1 million dinosaur bones driving back and forth. So, telling you guys, I don't see actually, if you really think about it, I don't see how one's going to hit first before the other. And that might greatly modify the trajectory of humankind. Direction we're going. Are we going to go to space, or are we going to start digitalizing ourselves? And it really depends on which one goes faster, in terms of reaching us first.
Yeah. Well, the problem with digitalizing a human mind is extremely, extremely difficult.
Oh, I understand that. It's extremely difficult. But it's it probably is possible. Probably more possible than getting to Alpha Centauri and those large number of people there. That's the thing. Which one's more believable to you? Can you mimic someone's brain enough so that it actually pretty much is that person in there? Or can you get to a different star system? That's how you expand. At one point, we're going to be faced with that. We'll have limited resources, X number of people on the planet, only an amount of resources that we have, and we have to start making choices. And at that point, that's when you can live forever in a digital format, or you can spread to the stars. Maybe we'll do both.
Okay. Well, I think we've had a good discussion tonight. We're going to kind of wrap it up now.
Okay.
Now we have what we traditionally do at this point is we have a recommendation. Each panelist gets to make one recommendation, and I do too. And it doesn't have to be anything associated with what we've talked about tonight. It can be anything that you found recently, came across recently that you thought was pretty cool. I have my recommendation in mind. Hopefully everybody else does. Who wants to go first?
I've got something. It's just a book I read recently, which is The Hunt for Vulcan by Thomas Levinson. It's quite a short book, but it's about the efforts in the 1800s to locate this missing planet that seemed to be influencing the orbit of Mercury, and because they'd had success in finding a previously unknown planet which was influencing the orbit of Uranus, which turned out to be Neptune, they thought, well, this an anomaly in the orbit of Mercury, and it must be caused by another planet even closer to the sun. So it's a really interesting history of that, and how, in fact, Einstein's theory of relativity eventually solved the problem, and there was no such planet. But it's a pretty interesting little book.
Who's the author again?
Not very long.
Who's the author again?
Thomas Levinson.
Thomas Levinson, Hunt for Vulcan. Okay.
Yeah, The Hunt for Vulcan. Yeah.
We'll have links to that in the show notes, folks.
Yeah.
Okay. Who wants to go next?
Okay, well, I've got one for you. It's a little trailer, basically, for the next session we're doing at the 67th IAC, the International Astronomical Congress. This is on the 27th of September this month. Elon Musk is purportedly going to announce his Mars colonial transporter architecture. So we've been waiting for this for a very long time. He tweeted today that he's probably going to have to rename it, because they found out now they've got the architecture down, they can actually go further than Mars. So he's obviously still very much intent on revealing it to us. Hopefully it will be 27th. So that'll be before the next podcast, and that's going to be really big. I don't know if we're going to beat. Hopefully, if he carries on at this pace, we'll beat the digitalization deadline where we're all on a hard drive. So. Right, me too.
Okay, who else? Nick, Roger?
I would like to recommend 4 papers, but I'll single out one of them just to give a title. There's a fellow at Boise State University by the name of Stephen J. Olson, who over the past couple of years has written 4 papers about what he calls aggressively expanding civilizations. So I'll recommend his Homogeneous Cosmology with Aggressively Expanding Civilizations, which appeared in the Classical and Quantum Gravity Journal. And there are other titles are Estimates for the Number of Visible Galaxy-Spanning Civilizations and the Cosmological Expansion of Life, and Long-Term Consequences of Observing and Expanding Cosmological Civilization. And there's another one. So there's at least 4 papers by this fellow, and they're quite relevant to what we've been talking about tonight.
Okay, we'll have the links in the show notes, folks. Nick's always good about sending me links. How about you, Roger?
I don't know. I'll just take whatever you guys. I just like listening.
Seen a movie lately that you like, or a TV show?
Well, yeah, I like big Star Trek fan. I know the new one's coming out, the streaming. How about possibilities on faster than light travel? I don't know. Okay,
well, that's all right. I mean, I kind of surprised you with this one, but
yeah,
this is a sort of a thing we do every episode. Okay, my recommendation, which I struggled with myself over, but I finally landed on the perfect one, I think, and I can't remember what it is. Oh, by the way, David, I'm a little bit angry with you and Marcia for recommending Orphan Black.
Oh, okay.
Now I can't stop watching the damn thing. Tatiana Maslany's performance is amazing on that show. Yeah,
she's so incredible. Yeah, she's incredible.
This girl from Saskatchewan just can just act like nobody else. But hopefully we'll see a lot more of her in the future. Anyway, that's not my recommendation because that Marsha's already put that one out and David seconded it. I third it. Now my recommendation is a podcast. Remember podcasts? Those things where you listen while you're driving to work in the morning. We've actually had the host on the show before. Liam Ginty is Voices from L5, and he also he recently had on there Roger Lubin from the University of California, Santa Barbara, who's working on Breakthrough Starshot, as well as some his own independent NASA funded stuff, and I recommend Liam's approach and perspective is very different from mine. So if you listen to the WoW signal, you'll probably like what you see on Voices from L5, hear from Voices in L5. You won't see anything. But it's really, really good stuff. And so I recommend that you tune into that podcast. I will put a link in the show notes. Okay. We are at the end of our show. Give everybody one last chance to make any comment or remark they wish to make. Let's start with Chris Prophet.
Oh, I'm just very happy with the whole show. I think it's very interesting to see the scale of things, and I mean we're just basically a blip in time. We're here and we're gone. We can't see of the larger space we're in. Basically, it's just too dark out there. But maybe one day when we get all digitalized.
Okay, David, Grigg.
Well, I might use the quote that I used to start the topic thread for this, which is from Thomas Mann's book, series of books, Joseph and His Brothers. Very deep is the well of the past. Shall we not call it bottomless?
Oh, I like that. Okay. Thomas Mann. Yes. Nick.
Building on what Chris has just said, I'd like to say that even if we are just a blip, we are a blip that has managed to reconstruct scales of time all the way up to the cosmological, and that's not too bad for a blip.
Okay. And our new panelist, Roger Wehbe.
To the future, guys. I think we are a blip, right? But I think we'll last a real long time. We'll continue to innovate, and human people are really smart, and I think we're going to last a long, long time.
All right. Well, thank you, Roger. Listeners, please let us know what you think about this episode and other episodes. You can comment directly on the blog at unseenpodcast.com. We are on Twitter at Podcast Unseen. We have a Google Plus listeners community. We have a subreddit for unseen listeners. All those are available for you to make your voice known, and we hope to hear from you. If you'd like to be on the panel, that is, as I mentioned earlier, this is an open participation podcast. All you have to do is come over to our Google Plus community and join, and you will get invitations to be on the panel about every 2 weeks. And we have a posted plan up through March of next year, and you can see what the times are. If the times are not suitable for your time zone, please let us know. You can email unseenpodcast@gmail.com, and we will try to arrange a time that you can participate in. We have done that before, and we'll be happy to do it again. And so I would encourage you to participate, to comment. Even if you don't want to be on the podcast, let us know what you think. Let us know what topics we should talk about. And this is not my podcast. This is your podcast. So, again, that's unseenpodcast.com. To learn more about our parent podcast, the Wow Signal, go to wowsignalpodcast.com. I would like to plug briefly that earlier this week we had Dr. Tabetha Boyajian in a hangout, and we talked to her a lot about the implications of the recent Gaia data release for the star that she's famous for. Some people call it Tabby star, some people call it Boyajian star. She refuses to call it either of those things. She calls it the WTF star.
WTF.
The Where's the Flux star. No, she was great. Roger was there. She's really, really helpful and eager to communicate. And we talked very frankly about the latest results and what they might mean, what they don't mean, and what hopefully future results will be more refined and we'll have more information. Also, Roger and I are both active on a subreddit for KIC 8462852. I'll put a link to that in the show notes, where if you want to talk about Tabby Star, go over there, and that's the place to discuss it. That's the most active I've come across on the internet. So, see you there. Again, it's here in the East Coast of the United States. It's the 16th of September 2016. This is episode 59 of the Unseen Podcast. I'd like to thank my panelists one last time. Roger Wehbe, Nick Nielsen, David Grigg, and Chris Profit. And we'll see you next time in about 2 weeks on episode 60 of the Unseen Podcast. Goodbye.